Okay, inverse functions. Basically what happens is, well, let me just talk about these 5 concepts at the top first. Okay. To find the inverse, you switch the x and the y. We're going to see that in our very first example. Actually, while we're here, let's do this one. To find the inverse, you switch the x and the y. If you're given a table, even if you're given coordinate points, all that you're doing to find the inverse is you're flipping them, you're switching them. So for instance here, if this had a coordinate point of -2, 4, which it does, to get to my coordinate over here, I would just switch the x and the y around. And I'm going to do that for every one of these if I was trying to find the inverse of this particular function, or maybe find out if it is a function or not. Okay, so if you're ever given to you in a table, just flip the x and the y values around. All the y's go to x, all the x's go to y's. Okay, or you can do them individually. Now that's the easiest one. The domain and range switch, well that makes sense because again, you're switching x and y values. If you're graphing it, we're going to reflect the original graph over the line y equals x. There's an easy way of doing that. We're going to talk about that in a little bit rather than trying to play the reflection game. Okay, the inverse is a function if it passes, ooh. Now we're used to doing the vertical line test to see if it's even a function or not. Now we're seeing if there's an inverse by using the horizontal line test, but the same rule still applies. If it crosses in one place, it passes. If it crosses in more than one place, it doesn't. And then, oh, here come the compositions again. So we get to see them again if some of you are still trying to sneak by and not think you're going to need them. F of g of x and g of f of x, both given a result of x. If you plug one into the other, you get x out as the answer. And we're going to take a look at that too. Okay, so we looked at the part 1 here. Now, I got to admit, when I looked at this one, I was wondering a bit what I was thinking when I got to the end. So for example 2 here, it says find the inverse of the function f of x equals 2/5 x minus 1/5. Graph the function and its inverse. We're going to come back to the graphing part, but I just want you to see how this works. So here's my original expression. I take out the f of x function and replace it with y. So we're sort of regressing a little bit because we're going out of function notation back to y. Interchange or switch the x and the y. So you'll notice from these two equations, I switched the x's and the y's around. That's all I did. And once I do, I'm going to solve it for y. Now here's the one thing I think is just a bad idea. I hate the way they wrote the answer. Nobody writes an answer that way. If I'm solving here for y, okay, I'm going to divide through by 2. So y would be 5/2 x plus 1/2. I can graph that. Nobody's going to try and graph 1/2 of 5x. That's silly. But if I did graph those, they're going to reflect on this line that's called y equals x. It's this slant that goes up to the right. And what that tells me is if I were to take my paper and fold along that red dotted line, I would get the exact same reflection. It's like the graph's looking at itself in the mirror. And that's how I can tell what's an inverse of something else. But again, we're going to physically do that in a little bit. For now, I want to do this stuff algebraically. So when we get down to the bottom, keep my steps in line here. When I'm doing these, always run the same things. My first step, if it's not in y equals already, would be to get it there, is to switch the x and the y around. Always my first job. Once I do that, I'm going to go ahead and solve for y. So just like normal, I'd want to, of course, add my 4 over because I need to isolate my y term first. And then I'll go through and divide by 2. Now, I'll be honest. Could you leave it as x plus 4 over 2? Yes, but since we're going to be graphing these some of the time, that's probably not the easiest way to look at it. I would say an easier way to be looking at it would be to look at it as 1/2 x and 4 divided by 2 is 2. I think that's more useful, because we're all used to graphing lines in slope-intercept form anyway. But that's my goal. This would be the inverse of this. If I were to graph both of them right now on a graph, my graphing calculator, we'll just kind of let you see how this works. So if I were to take this and say, okay, my first equation's y equals 2x minus 4. My second one is y equals 1/2 x plus 2, and graph them. Now, I'm purposefully not putting my y equals x graph in here yet so you can see this, but you'll notice if I were to split it right down the gut here, I'd have symmetry. Oh, crap. That's why you don't want to erase. Because if I just put the line y equals x in, notice that basically the one that's splitting it right down the middle, that's my reflection. So if I looked on either side of this line, I see the reflection of the same thing on both sides. And that's what we're trying to accomplish here, except here we're doing it algebraically. Oh, so whenever I'm doing these, it's the same thing. Flip-flop the x and the y, and then it becomes get y alone. Now sometimes that's easier than others. So for instance here, I'd minus my 6 over. And again, it's a personal choice, but again, if we can do it in one step, that's great. What I would want to do here, of course, is multiply by the reciprocal, which would be negative 3/2. So y would equal negative 3/2 x. And then again, this is the detail work some of you got to slow down on. Negative 3 times negative 6 is 18, divided by 2 is positive 9. And that would be my inverse. And one other thing I'll mention about the inverses, because book to book and section to section this changes all the time. Sometimes instead of saying y equals, they may say f of negative 1, or you may see y of negative 1. Now that negative 1 here isn't an exponent, it doesn't mean flip it, it's a label saying this is the opposite, this is the inverse, because what do you do when you see a negative exponent? Normally you flip it, you take the inverse of your answer. So for any of these, we're just going to keep playing the flip game. Flip x and y, isolate my y term first. And again, how you get to writing that final answer is going to be your choice. Like here, I know I got to divide both sides by 2. If I want to write it and leave it in this fraction form, because I see what the next step's going to be, I see that I'm going to have to take a square root. Now remember, just because we're graphing, and this may be new to some of you, doesn't mean that when I take the square root of a quadratic, I don't need plus minus. We are actually going to be graphing plus minus functions. And it's going to be fun because they look like parabolas when you do it, except they're turned sideways. But we'll talk about that when we get to the graphing here in a couple of minutes. But those are the type of things I want you thinking about. But as long as you have the general idea working, ooh, this is going to be fun. And if some of you just hate dealing with the fractions, or every time you see a fraction you just want to put it in the calculator and you're really not sure if your answer makes sense, this is one of those times that if some of you despise fractions, it's not the worst thing in the world to go ahead and multiply this out. So what we're going to do here is I'm going to... So here, if you are a despiser of fractional stuff, knowing you're going to have a fraction, you're going to be multiplying or dividing by another one, I don't care, and it takes one step, but it may make life simple enough for you that you don't have a problem. If I multiply through by 5, here I'll multiply times the x, but here it'll just get rid of all of my fractional stuff. And now I can still go ahead and solve for y. Am I going to end up with a fraction in the answer? Yeah. But at least going this way, I don't have that fraction until the very last step when I divide both of these by 2. And I get my inverse that way. But again, the choice is yours. If you're comfortable with fractions, you're like, shoot, I don't care. Just keep rolling along. Okay, that keeps life simple enough for everybody. So that's something to ponder. You're like, okay, inverses algebraically. What else you got? Well, our second rule. Oh, I'm sorry, yes.
So I was wondering why you actually distributed the fraction through all of number 5. Like, I would never say my concept plus 2. Then if you didn't do that number 4, you just made it x times 6.
Okay, good question. So why did I choose not to simplify this into 1/2 x minus 4 here, and I did on this one? Basically, I'm trying to show they're interchangeable. If I was going to go and I was graphing these, either using a calculator or doing it on my own, when I just have a y equals, I'm just used to slope-intercept form. To be perfectly honest, if you have a radical, it's going to be easier to type it into the calculator, leaving it as the fraction. But even if I typed it in, the calculator is 1/2 x minus 4, I'll still get the same thing. Okay? Yeah, some of you got to wave me down sometimes. I get so having fun and into this that I don't pay any attention. I'm like in my own little world up here sometimes. All right. So, part 2, this is the simplest one. The inverse is a function. Now, again, you're not having to graph the inverse yet, but the inverse of a function if it passes the horizontal line test. So in other words, just like we did when we were doing the vertical line test, if I can draw a horizontal line through the original graph, and it's only crossing at one point, then yes, the inverse would be a function. Which is strange because if I ran this through the vertical line test, it wouldn't pass it, but its inverse does. Kind of strange. But again, it doesn't matter where I draw it through. I'm not looking for the exception, but here, okay, I think I've proven my point. It's going to go through more than one. This one, its inverse would not be a function. It doesn't pass the horizontal line test. But just to show I can keep moving around, yep, only one spot. This one's good. And that's all you've got to do on this. If it just asks you, is the inverse going to be a function? Run the horizontal line test, see if it works, and you're done. You're like, shoot, I wish they were all that way. Another way that we can do this, if we don't have a graph, is through verification. If f of x and g of x are inverses, then f of g of x will equal x, and g of f of x will equal x. In other words, if I plug the g function into f, the answer is going to come out x. But if I also plug the f function into g, the answer is going to come out x. And if it doesn't, well, then they're not. So here's how this works. Okay, we're going to test out f of g of x first. Now, remember, f of g of x means it's f of, and I'm literally going to plug in that g of x function into f. Now, do I have to write it out this way? No, but I want you to see what I'm plugging in. So this is going in right there. So I've got 3 times 1/3 x minus 2 plus 6. The only thing that changed was what's in the parentheses went in for x. Everything else stayed the same. Because now if I simplify it, 3 times 1/3 would just be x. 3 times -2 is -6 plus 6. Well, -6 plus 6 cancels. I just get x. Okay? So for the f of g of x part, it passes. So you're saying, you mean sometimes it might not pass both? It might pass one? Maybe. That's why we check them both. So if I switch gears and plug in f of x for g, again, that means I'm going to plug 3x plus 6 in for x in my g of x. Like, all right. So let's see. That would be 1/3 3x plus 6 minus 2. And then I just distribute and simplify. 1/3 of 3x is x. 1/3 of 6 is 2 minus 2. 2 minus 2 is 0. I'm just left with x. Yes, these are inverses. But it has to work for both. If it only works for one, no good. If you ever see that there's one that doesn't work, well, then you're just done with that. So let's say I get to this next one, and I won't do this part this time. We'll kind of just see what this looks like. So I'm going to plug g of x into here. Okay, so I've got 4 plus the square root of x minus 4 squared, because this is going in there. You're like, ew, but again, this isn't bad. Squared and square root are opposites or inverses, so they just cancel. 4 plus x minus 4. Oh, 4 minus 4 cancels. It's just x. Okay, that one's good. But again, you have to show this. And again, take the time to plug it in. So, does the reverse work? Well, let's see. So, f is going into g. So, x gets replaced by 4 plus x squared. And then minus 4. Well, 4 minus 4 is 0, so it's the square root of x squared, which is x. Okay, cool. So those are inverses. That's a yes. You're like, all right, maybe this might be all right. So I keep looking at these, and I'm like, there's got to be one here that's not going to work, because he's not going to have all these work. You know, let's see if this one's the one. So f of g of x, let's see here. So g of x is going in. So 2 times 5x minus 2 plus 3. Distribute that out. X minus 4 plus 3. Uh-oh. 10x minus 1. That does not equal x. I don't even have to do the other one. It doesn't matter if the other one works. They both have to work for them to be inverses. So that one doesn't equal x. Done. Finished. Don't care. Not dealing with the other one. But let's see if this last one works. All right, so gn here. Cubed root of x minus 5 cubed plus 5. Okay, cubed and cubed root. Inverses. I'm just left with what's underneath. Minus 5 plus 5 cancels. We're good through the first part. Let's see. Plug f into g. Okay, so the cubed root of x cubed plus 5 minus 5. Because again, this is my x, and the minus 5 is still there. Those guys cancel. The cubed root of x cubed is x. Woo-hoo. Okay, so you do have to test both. Because there is a possibility that you could get one and not the other. So never, 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 ever, never make the assumption. Okay, let's see here. So next we've got graph each function. Use the graphing calculator. I will. And use the horizontal line test to determine whether it is a function. Okay. So let me clear these out. Maybe. Clear. There we go. So x squared plus x graph. Is that going to pass the horizontal line test? No. You're like, I just get to say no? Yes. I'm just going to make quick sketches of these as I go so we can actually see if we looked at them later. Well, why was it no? I don't know why it was no. Well, now you will know why it was no. Okay, let's see here. Horizontal line test, what say you? Because anywhere I put a horizontal line through here, it's only going to be going through one point on my graph. So when in doubt, and if you're ever in doubt with one that you do, this is a quick way that you can double check. Yes, no, maybe, it depends. No. Going through a lot of places. So again, graphically we can do it even when we have that information. So next, we're going to find the inverse of this function. Now the x is greater than or equal to 0 is only a descriptor. That's not part of what I'm trying to solve. So when I'm looking for the inverse, okay, I'm going to go ahead and change f of x into y. But once I've done that, switch the x and y, and solve for y. So why was the descriptor necessary? Why does x have to be greater than or equal to 0? Look at what your new y equation is here. What would happen if x was a negative value? Right, we'd get I working here. So, x less than 0 would be imaginary. And again, get used to having things where you have to explain things. Some of you continue to want to skip those problems or just write like a one-word answer like yes, no. I'm like, what's that telling me? It's not telling me anything. Because if you can explain it, it's going to click better. And again, as we're looking for these inverses, there's different ways you can write them. Again, f of x gets replaced with y. Switch them. And now work on getting y on a side by itself. So minus the 1 over. I'm going to divide by 2, and I see that cubic coming, so I'm going to choose to leave it in its fractional form. But you don't have to. If you want to have 1/2 x minus 1/2, you can. Am I going to have plus minus this time? It's one of those answers.
Maybe.
Oh, gracious. No, I said it was yes or no was one of the answers. No, okay? Right, on odd roots, I don't need plus minus. Even roots, I do. Because again, I can square a negative number and it comes out positive still. These, I don't have that same option. So let's see. 19, I'll explain. Explain how to use the horizontal line test to determine if an inverse relation is an inverse function. Ew. What's something have to do to pass the horizontal line test? Okay. Okay. So it intersects the function at only one point. If it crosses more, it's not going to have that. And I actually saved the most fun part for last. At least I'm hoping you're going to agree with me. Graphing the inverse actually lets you see why this is and how it works. So this is kind of fun. All right. Last part. It can be. So I've got to go ahead first and find what my inverse is going to be. And again, we can call that f of -1, y of -1, whatever we want to do. But again, so we're going to switch y in for f of x. Then we're going to flip those guys around, and we're going to solve for y. So we add the 4 over. And again, since I notice here it's just going to look like a regular graph, I am going to break it down. So when I divide by 2 here, I'm going to have 1/2 x, and 4 divided by 2 is 2. Okay, so that is my f of -1. Now here's where the fun part comes in. When you graph the function and its inverse, now these are just 2 lines, so it's going to be really easy to see. So 2x minus 4, okay, get my y-intercept down there at -4. And then again, slope is always a fraction. So I go up 2 and right 1. And I'm going to go a little dot crazy here because I really want an accurate picture so I can really see how this is working. Or if you have a straight edge or you really feel confident you can draw a straight line, you can go ahead and do it that way. So what's going to happen here is I'm going to graph both of these. Now I'm going to graph my inverse. So up 1 and over 2. May have an occasional point overlap. That's okay. And you don't have to go as nuts as I do with the dots. It just helps me make a really straight line. But what I want you to see here is, in case you don't necessarily see the symmetry going on, the inverse part of this, if I were to draw a line, I'm going to do a dotted line through what's called y equals x, which basically means your x and y values are identical. And I'm not going to totally connect these. I'm just going to use the dots to let you see the symmetry involved here. If I were to fold my paper along that dotted blue line, they would end up right on top of each other. Or if I were to put a mirror there, I'd also see that I'd see the exact same thing going both ways, if I've done it right, and if they're inverses, and they are. So that's kind of cool. Now, the last thing that I sort of want to let you see here, which is kind of, this is the one that I have the most fun with, is graphing the inverse of this guy. So let's do this. All right, yn for f of x. Let's switch them around. And now I got to start working on getting y by itself. Do not FOIL this out. Oh, please do not FOIL this out. Too much work. But how am I going to get to my y if I'm not going to FOIL it out? How do I dump the squared? Take the square root. Okay, but remember, when I'm doing a quadratic, you're like, ooh, this is a new one. And I still got to move that 3 to the other side. Here's where the fun begins. Okay, so I look at this, and I'm like, all right, so what's my deal? I'm going to graph this guy first, my original. You're like, okay, it just looks like a normal like parabola thing. Let me steal some points here so I can make this go a little bit simpler. So I'm just going to basically take the points that they give me that are going to fit on my graph. Okay, so there's my original f of x. You're like, now how am I supposed to do plus minus on here, though? That's kind of weird. We're going to do them separately, but I want you to watch these one at a time. So for instance, I'm going to do 3 plus the square root of x minus 5. And that's the only one I'm going to graph at first, because I want you to see how this comes together. So if I graph this, that's only half a parabola, though. Yes, it is. But watch and be... No, that's not what I wanted to do. Get too excited, start erasing things. Okay, let's try this again. Now I'm going to do the same, but I'm going to get my minus in. So here's where how my plus minus works when I'm doing this. X minus 5. This is what's fun. Graph. All of a sudden, I get that parabola. Now, you might think there's a hole in there, but there's not. And here's how I know. You're like, whoa, there's way too many things going on, Harty. Okay, my y of 1 is my first one that I already have. So all those errors means my values don't start until I get to here. But notice, when I'm at 5, both of them have a y value of 3. So I go to 5, 3, I put a dot. Then as I start moving down, when I get to 6, it says there's a y value at 4 and a y value at 2. And decimals, okay. And then I get to 9, it says 5 and 1. And when you connect the dots, there's your parabola. And if I were to make my dotted y equals x line to C, oops, I got a little off there. I can see that if I were to flip over, they would end up basically on top of each other. And again, 22 and 23 we've talked about in like exaggeration on how we find those. Because again, if you do want to answer on 22, they reflect along that line y equals x. That dotted blue line that I keep putting in on these. That's how they're related graphically when we look at the graph. And then we talked about the 3 steps to find an equation from an inverse. F of x becomes y, switch x and y, solve for y, good. So the actual work for this is down at the bottom of this page. So the note packet kind of goes with the homework this time. This will end up being assignment number 2 in homework check 11 number 2. And very, very soon, I want to make sure it's tomorrow before I say it. Yes. One of our favorite things is coming back tomorrow, factoring. Yay. Woo. Thank God. That might be a first.